In 1980, NASA engineers made a decision that would end humanity's ability to see anything else through Voyager 1's eyes for the next 10 years. They shut the cameras off. Not because anything broke, not because the mission failed. They shut them off on purpose because there was nothing left in front of the spacecraft to photograph, and every photo it took was burning power and memory the spacecraft would need for the rest of its journey out of the solar system. Before that happened, though, Voyager 1 captured a set of images that changed how humanity understood its own solar system permanently. Here's what it saw, in order, and why those images still matter today. Voyager 1 launched on September 5th, 1977 from Cape Canaveral, actually 16 days after its twin, Voyager 2, even though it was numbered first, because Voyager 1 was placed on a faster trajectory that would let it overtake its sibling and reach Jupiter first. Both spacecraft were built to take advantage of something that only happens once every 175 years. A rare alignment of the outer planets that let a single spacecraft use each planet's gravity to slingshot toward the next one, cutting a trip that would normally take decades down to a fraction of that time. Voyager 1's assigned route was Jupiter, then Saturn, then out of the solar system entirely. Voyager 2 was sent on the longer road, eventually reaching Uranus and Neptune as well. But it's Voyager 1's imagery from Jupiter and Saturn, captured in the 2 years before its cameras went dark, that produced some of the most important photographs in the history of planetary science. Let's start with Jupiter, because this is where Voyager 1 began rewriting textbooks almost immediately. Voyager 1 made its closest approach to Jupiter on March 5th, 1979, after a flight of roughly a year and a half. Before Voyager, humanity's best images of Jupiter came from the Pioneer 10 and 11 flybys earlier in the decade, and those were valuable but limited, grainy by comparison, and captured with far less sophisticated instruments. Voyager 1 carried a much more capable imaging system, and as it closed in on Jupiter, it began sending back photographs with a level of detail nobody had seen before. The single most famous image from this encounter is Jupiter's Great Red Spot, photographed in extraordinary close-up detail for the first time in human history. Scientists had known about the Great Red Spot since the 17th century, visible even through early telescopes as a reddish oval on Jupiter's southern hemisphere. But nobody had ever actually seen what it was made of, how it moved, or how it interacted with the bands of clouds around it. Voyager 1's photographs revealed the Great Red Spot as a massive, churning storm system larger than Earth itself, with visible turbulent structure at its edges where it collided with the surrounding cloud bands. You could see individual eddies spinning off from the storm's boundary, swirling into the neighboring cloud belts. It was the first time humanity had a genuine close-up photograph of weather on another planet, and it looked alive. A storm that had apparently been raging continuously for centuries, caught mid-motion in a single frame. Voyager 1 also captured detailed images of Jupiter's cloud bands themselves, the alternating light and dark stripes that wrap around the planet. Up close, these bands turned out to be far more complex than the simple striped appearance visible from Earth. They showed intricate wave patterns, swirling vortices, and turbulent boundary zones where bands moving in opposite directions rubbed against each other. Some of these images captured what looked almost like marbled paint swirling on the surface of the planet, an effect created by Jupiter's violent atmospheric winds, some of which reached speeds of hundreds of miles per hour. But the images that arguably had the biggest scientific impact from the Jupiter encounter weren't of Jupiter itself. They were of its moons. Voyager 1 photographed Io, the innermost of Jupiter's 4 large moons, and what it found stunned the mission scientists. Io appeared in the images as a mottled world of orange, yellow, and black, unlike anything else photographed in the solar system up to that point. Then, almost by accident, one of the imaging scientists analyzing the photos, Linda Morabito, noticed something strange in the background of one image, a faint plume, rising off the edge of Io's disk against the black of space. Further analysis confirmed it. Voyager 1 had photographed an active volcanic eruption in progress on a moon 390 million miles from Earth. It was the first time an active volcano had ever been observed anywhere in the solar system outside of Earth. Before this discovery, most scientists assumed that small rocky moons would be geologically dead, too cold and too small to sustain any kind of internal activity. Io shattered that assumption completely. Follow-up images from Voyager 1 identified multiple plumes erupting simultaneously from Io's surface, some reaching hundreds of kilometers into space. It turned out Io was the most volcanically active body anywhere in the solar system, its surface constantly resurfaced by eruptions driven by the intense gravitational stresses of being squeezed between Jupiter and its neighboring moons. Voyager 1 also imaged Europa, the icy moon just beyond Io, and although its photographs were less detailed than what Voyager 2 and later missions would capture, they showed enough to reveal something genuinely strange, a surface crisscrossed with long, dark linear cracks, but almost no visible impact craters. On a body sitting in a region of space regularly bombarded by debris, the smooth, crack-covered surface with few craters told scientists something important. Europa's surface was young, geologically speaking, constantly being resurfaced by something happening underneath it. That observation, made from Voyager 1's initial photographs, planted the first seeds of what would become one of the most important questions in modern planetary science: whether Europa hides a liquid ocean beneath its icy shell, and whether that ocean could support life. Beyond Io and Europa, Voyager 1 also captured images of Ganymede and Callisto, Jupiter's two largest moons. Ganymede, the largest moon in the entire solar system, bigger even than the planet Mercury, showed a surface split between older, heavily cratered dark terrain and younger, brighter regions, crossed with long grooves and ridges, evidence of past tectonic activity reshaping its icy crust. Callisto, by contrast, appeared saturated with impact craters from edge to edge, more densely cratered than almost anything else photographed up to that point in the mission, suggesting a surface that had remained largely unchanged for billions of years, untouched by the kind of internal geological activity reshaping its neighbors. Together, the four large moons of Jupiter that Voyager 1 photographed told a story nobody had anticipated going into the mission. Four worlds of similar size, orbiting the same planet, yet each one geologically distinct from the others, one racked by volcanic fire, one potentially hiding an ocean, one scarred by ancient tectonics, and one seemingly frozen in time since the early solar system. That single insight, that moons this similar in size and origin could turn out this different from one another, reshaped how planetary scientists thought about moons throughout the entire solar system, not just at Jupiter. After Jupiter, Voyager 1 continued on toward Saturn, arriving for its closest approach on November 12, 1980. This was Voyager 1's final planetary encounter, a deliberate choice built into its trajectory. To get a close flyby of Saturn's largest moon, Titan, mission planners had to send Voyager 1 on a path that would bend its trajectory sharply out of the plane in which the planets orbit the Sun. That maneuver gave scientists an up-close look at Titan, but it also meant Voyager 1 could never visit another planet again. Once it passed Saturn, its path was permanently set, arcing up and away from the solar system's orbital plane, headed out into interstellar space with nothing else ahead of it to photograph. But before that happened, Voyager 1 delivered the most detailed photographs of Saturn's ring system ever captured up to that point. From Earth, Saturn's rings appear as a handful of broad, flat bands. Voyager 1's photographs revealed something completely different. Thousands of individual, narrow ringlets, nested within each other like grooves on a vinyl record, some with sharp, crisp edges, and others with braided, twisted structures that puzzled scientists for years afterward. The images showed gaps in the rings carved out by the gravitational influence of small moons, and dark radial features called spokes that seemed to move across the rings in ways nobody fully understood at the time, and which are still studied today. What had looked like a simple, elegant structure from telescopes on Earth turned out, up close, to be an almost impossibly intricate system, more like a delicate machine than a simple band of ice and rock. Voyager 1 also photographed Saturn's atmosphere in detail, revealing banded cloud structures similar in principle to Jupiter's, but far more subtle and pale, and it captured images of several of Saturn's moons, but its single most significant target at Saturn wasn't the planet or the rings, it was Titan. Titan is the second largest moon in the solar system, and going into the Voyager 1 encounter, it was one of the most mysterious bodies scientists had ever tried to study, because it's the only moon in the solar system with a substantial atmosphere. Voyager 1's camera turned toward Titan, expecting to finally photograph its surface in detail. Instead, it photographed something almost anticlimactic at first glance and profound on closer study. A featureless, hazy orange ball. Titan's atmosphere, thick with nitrogen and laced with organic compounds, turned out to be so dense and so filled with photochemical haze that Voyager 1's cameras couldn't see through it to the surface at all. The image of Titan that came back was essentially a smooth orange sphere, with almost no surface detail visible whatsoever. That disappointing image ended up being one of the most scientifically consequential of the entire mission. The thick orange haze itself became a subject of intense study because its chemistry, nitrogen combined with methane and other hydrocarbons, cooked by sunlight into complex organic molecules, resembled, in a general sense, the kind of prebiotic chemistry scientists believe may have existed on early Earth before life began. Voyager 1's image of a featureless orange moon effectively launched decades of scientific interest in Titan as a natural laboratory for studying the chemistry that might precede life, an interest that eventually led to the Cassini-Huygens mission's landing on Titan's surface more than 2 decades later, finally revealing the methane lakes, rivers, and dune fields hidden beneath that haze Voyager 1 could never see through. It's worth understanding, briefly, what these images were actually captured with, because the technology itself is part of why these photographs feel the way they do. Voyager 1's imaging system used 2 Vidicon cameras, a wide-angle camera and a narrow-angle telephoto camera, built around technology that, even by 1977 standards, was already a generation behind what television broadcast cameras were using. Each image wasn't captured all at once the way a modern digital photo is. It was built up incrementally, scanned in narrow strips and transmitted back to Earth as raw data, then reassembled and color processed by scientists on the ground, often combining multiple black and white exposures taken through different color filters to reconstruct a full-color image. The distinctive look of Voyager's most famous photographs, slightly grainy with visible processing artifacts around the edges, isn't a flaw. It's the visible signature of images that were built piece by piece across a radio link spanning hundreds of millions of miles using instruments that predate the personal computer. With the Titan flyby complete, and with Voyager 1's trajectory now permanently bent out of the plane of the planets, there was nothing left ahead of the spacecraft to photograph for years, possibly decades. NASA made the call to power down the imaging system. Every instrument on Voyager 1 draws power from the same source, a radioisotope thermoelectric generator, essentially a nuclear battery that slowly loses output over time as its plutonium fuel decays. With no more planets to photograph, keeping the camera system powered on and actively used would have wasted energy the spacecraft would need for its other instruments, the ones measuring cosmic rays, magnetic fields, plasma waves, and the properties of interstellar space, all instruments critical to the spacecraft's real long-term mission once it left the solar system behind. So, in 1980, not long after the Saturn encounter, Voyager 1's cameras were deliberately shut off. For a decade, the cameras stayed dark. Then, in 1990, at the urging of astronomer and science communicator Carl Sagan, who had been a member of the imaging team since the mission's earliest planning stages, NASA agreed to one final act with the cameras before shutting them down permanently. Sagan had been advocating for years for Voyager 1 to turn around and take a photograph of Earth from the edge of the solar system, arguing that the image itself, beyond any scientific value, would carry enormous meaning for how humanity understood its own place in the universe. Many engineers on the mission were skeptical. There was genuine risk in reactivating a camera system that had been powered down for 10 years, and pointing the camera back toward the sun risked damaging the optics with direct sunlight. But on February 14, 1990, from a distance of about 3.7 billion miles from Earth, roughly 40 times the distance from the Earth to the Sun, Voyager 1 turned its camera around and captured a series of 60 images making up what became known as the family portrait, photographing several planets of the solar system as tiny points of light scattered against the blackness of space. Within that series was a single frame that became one of the most famous photographs ever taken. In the image, Earth appears as a single pixel, less than the size of a period at the end of a sentence, suspended in a scattered ray of sunlight refracted inside the camera's own optics. A beam of light that happened to fall directly across the pixel representing our entire planet. Sagan later gave the photograph its name, the pale blue dot. He would go on to write an entire book built around the meaning of that image, describing Earth as it appeared in the photograph as a mote of dust suspended in a sunbeam, and using it as the foundation for one of the most quoted passages in the history of science communication, a reflection on the fact that every human being who has ever lived, every war ever fought, every civilization ever built, existed entirely within that single pixel of light. The pale blue dot wasn't the only meaningful image in that final 1990 sequence. The family portrait also included images of Venus, Jupiter, Saturn, Uranus, and Neptune, each captured as a small dot of light against the surrounding darkness, along with the sun itself appearing not as a blinding disk, but as a comparatively small, bright point. A visual reminder of just how far Voyager 1 had already traveled from its starting point. Mercury and Mars were excluded from the final sequence. Mercury because it was too close to the sun's glare to photograph safely, and Mars because it wasn't in a favorable position relative to Voyager 1's viewing angle. But taken together, the family portrait images did something no photograph had ever done before. They showed the solar system not as a diagram in a textbook, not as a scale model, but as it would actually look to something impossibly far away, looking back, reducing the entire known world humanity had ever known to a scattering of faint points of light in an otherwise empty frame. After capturing that final sequence, Voyager 1's cameras were shut off again, this time permanently. The imaging system itself was eventually powered down entirely, and in the years since, its software has effectively been retired from the spacecraft's operating systems as engineers have worked to conserve every remaining watt of power for the instruments that matter most to Voyager 1's ongoing mission. There will be no more images from Voyager 1, ever. The pale blue dot and the rest of the family portrait sequence are permanently the last photographs the spacecraft will ever take. But Voyager 1's journey didn't end there. Its imaging mission did, but its scientific mission kept going. In August 2012, Voyager 1 became the first human-made object to cross the heliopause, the boundary where the constant outward flow of charged particles from the sun gives way to the interstellar medium, the space between star systems. That crossing was confirmed not through any image. The cameras had been dark for over 2 decades by then, but through changes detected by Voyager 1's plasma and particle instruments, the same instruments NASA had prioritized keeping powered when it made the decision to shut off the cameras back in 1980. In a very real sense, that decision, made 3 decades earlier, was what allowed Voyager 1 to still be functioning and still be transmitting data by the time it reached that historic boundary. Voyager 1 remains to this day the most distant human-made object from Earth, traveling at roughly 38,000 miles per hour, adding more than 300 million miles to its distance from Earth every year. Its radio signals, traveling at the speed of light, currently take more than 20 hours to reach ground stations on Earth, meaning any command sent to the spacecraft takes nearly 2 full days for scientists to know whether it worked. The spacecraft's plutonium power source continues to decay at a predictable rate, and NASA engineers have had to make an ongoing series of difficult decisions over the years, shutting down one instrument after another to keep the spacecraft's remaining systems powered as long as physically possible, extending the mission's life a little further with each individual sacrifice. Looking back at the handful of years when Voyager 1's cameras were actually active, what stands out is how much scientific and cultural weight came out of such a narrow window of time. The Great Red Spot, seen up close for the first time in human history. The discovery of active volcanism beyond Earth, found almost by accident in the corner of a photograph nobody expected to be. Interesting. The strange, cracked, crater-poor surface of Europa that quietly opened one of the biggest open questions in the search for life beyond Earth. The intricate, impossibly detailed rings of Saturn, revealing structure nobody had guessed at from Earth-based telescopes. The frustratingly opaque orange haze of Titan, which turned out to be more scientifically interesting precisely because of what it hid rather than what it showed. And finally, a single scattered pixel of light, representing every human being who has ever lived, captured almost as an afterthought, at the literal edge of what the spacecraft's cameras could still usefully see. None of these images could be recreated today by simply sending another spacecraft to the same spots and photographing them again. The circumstances were unrepeatable, a rare planetary alignment that only comes once every century and 3/4. A spacecraft built with instruments that were, for their era, at the absolute cutting edge, in a series of scientific and engineering decisions made under real uncertainty about what to prioritize and what to sacrifice. The choice to turn off the cameras in 1980 wasn't a failure or a limitation forced onto the mission. It was a calculated trade-off that ultimately allowed Voyager 1 to keep functioning for decades longer than it otherwise would have, all the way out past the edge of the solar system and into interstellar space, a journey that arguably wouldn't have been possible if the spacecraft had kept spending its limited power reserves on a camera with nothing left in its field of view worth photographing. What Voyager 1 left behind, in that narrow window between 1979 and 1980, and then again for one final afternoon in 1990, is a set of photographs that fundamentally reshaped how scientists understood the outer solar system, and reshaped, at least for a moment, how a great many people understood their own place within it. A storm larger than Earth, still spinning after centuries, a moon violently alive with volcanic fire nobody expected to find. Rings built with more structure and complexity than anyone had imagined. A hazy orange world hiding chemistry that might resemble the earliest chapters of life itself. And a solar system, our solar system, reduced to a handful of scattered points of light against an empty black background, with everything any human being has ever known contained inside a single pixel, caught in a stray beam of light on its way out of the frame. Voyager 1. How? Voyager 1 is still out there right now, decades past the moment its cameras went dark for the last time, still transmitting, still traveling, still the furthest thing humanity has ever built, carrying with it a golden record of sounds and images meant to represent Earth to whoever or whatever might one day find it. A spacecraft that stopped looking back with its cameras a long time ago, but never once stopped moving forward.